This is the first lecture on computer buses for Comp 375 Computer Architecture and Organization at North Carolina A&T State University. A bus is what connects all the parts together on the machine. It connects the CPU, the memory, the I/O controllers. In a simple version, it's just a bunch of wires, a bunch of parallel wires, one for each bit, with rules for putting the information on and retrieving it from the wires. In our basic computer diagram, the bus is that parallel line along the bottom that connects the CPU, the memory, and the I/O controllers. Typically, there's many I/O controllers, but I only showed one in the diagram. Real buses are a lot more complex. Here's a picture from Intel in the description of the Z87 chipset that controls the bus. You can see there's all sorts of interfaces to the bus. Computers have many different types of buses. We talked about a bus connecting the different registers in the microcode system. That's a completely different bus than we're talking about today. The system bus is on the motherboard or the printed circuit board of the computer, and it can be up to about a foot in length. Here's a picture of a motherboard or the computer circuit board, and it shows many plugs that allow you to plug things into the bus. Many other devices are built into the bus, but sometimes computers are built with the ability to add more components. This is what it looks like from the side, where you might buy an extra device. For instance, a graphics card that you want to add to your computer, and you plug it into the socket, and that's a connection to the bus wires. We're talking about the internal buses of the computer. They run very quickly, about 20 gigabytes per second. Now, they're significantly different than the external buses. A USB is a universal serial bus, and it's a connection that allows you to connect all sorts of different devices to your computer. There are different speeds. USB 2 runs at 280 megabits per second, whereas USB 3 runs at 5 gigabytes and 3.1 run at 10 gigabits per second. Now the USB cables can be up to 5 meters in length, while the bus on the circuit board is only about a foot, maybe 10 inches in length. Also, your USB allows you to pull things out and plug them in at any time. You can't do that on the internal bus. You got to turn the computer off before you change anything. There are different aspects of a bus, and we will cover each one of these in detail. There are different wires of a bus. Most of them carry data across between the different devices, memory and the CPU or the I/O controllers. There's also address information. What address do you want from the memory? And then there are several bus lines that control the access to the bus, whether you want to read or write to a data value, whether the bus is ready, whether what you've requested is available, whether there's an interrupt or the interrupt has been acknowledged, along with a clock signal. When we speak of the width of the bus, we talk about the number of lines, typically the number of data lines that the bus can have. You can put one bit on each wire because the wire is either charged up to voltage or grounded down to indicate a 1 or a 0 bit. The more wires you have, the more bits you can transfer in parallel. You also have wires for the addresses. The more address lines you have, the more wires you have to address the memory. The number of address wires determines how much memory you can access. Because each wire represents one bit, it's 2 to the number of wires that determines the maximum amount of memory. 32-bit processors that have a 32-bit address space can access 2 to the 32 or 4 gigabytes, One of the big advantages of switching to the 64-bit systems like we have today from the 32 bits or older is that they could extend past the 4 gigabyte limit. This is easy to calculate. Okay, 20 bits is a megabyte, so 2 to the 20th is mega. So the answer is going to be A or B because it's megabytes. 2 to the 4 is 16, so it'd be 16 megabytes. So the answer is A, 16 megabytes. Historically, a lot of computers could address 16 megabytes because they had 3 bytes or 24 bits of address space. Powers of 2 again. It's important to remember your powers of 2. Different computers have different width buses. The 32-bit Pentium processor had 64-bit data bus. The Itanium, which is a 64-bit processor, has 128-bit bus. The old 8086, which made the first IBM PC, had only 20 address lines, and so it could only address up to 1 megabyte. And in fact, the max amount of RAM you could have in the machine was 640K because the other portion of the memory was used for other devices. Some buses use the same wires for addresses and data, and some buses use separate wires for address and data. A dedicated bus has dedicated wires for address and dedicated wires for data, or multiplex shares. And sometimes the wires are used for data and sometimes the wires are used for addresses. So if you want to store information into memory from the CPU, you can put the address on the address lines, the data on the data lines, and write it at the same time. With a multiplex bus, you have to put the address on at one time, and then the next time period, put the data on. I'm dedicated to learning about buses. Why don't you take the bus and get out of here? Multiplex buses require fewer wires, and therefore fewer connections to the CPU chip. For a given number of pins, it's usually advantageous to be able to transfer more data. So you want more pins. So a multiplex bus might do that, but then again, multiplex buses may take longer because you have to share the wires. Data moving between the CPU and the memory is done like a store or a read. Whereas you write memory to the bus and then to memory. CPU writes it to memory or reads it from memory. The I/O devices do the same thing. Looks like they are reading and writing from memory as if the CPU. Basically, if you want to get information from memory or a controller, you set the control lines to tell the bus you want to access the bus. That you are the device that wants to access the bus. Then you put the address in the address lines, tell the memory system that you want to read. Then you have to wait until that's over because it doesn't happen immediately. Finally, the values are available on the bus. You read those values in and then set the control lines to allow some other device to use the bus. There are multiple devices competing to use the bus. You have all your I/O devices, your memory, your CPU, all competing to use the bus. Storing information from the CPU or an I/O controller into memory is just about the same process. Only in this case, you're putting the data from the device into memory. Now, there's only so much information that you can pass across the bus at one time, and frequently the CPU or I/O controllers want to send more data across the bus than it can do in a single cycle. So it has to make multiple transfers. It will have to take several cycles to transfer the information across the bus. And some of the devices are not as fast as the CPU. Typically the CPU runs faster than any other device on the machine. So when the CPU wants data from RAM, it'll have to wait for it. So it sends the request, and then a few cycles later, the data will be available. There's typically a bus clock. This is a oscilloscope picture of what a bus clock might look like. There are time periods going along, and each cycle is one clock cycle there, goes up, down, and then going back up again. These keep all the devices synchronized together. We're computer science, not computer engineering. We don't need no silly scope. We're just working on the concepts. If we look at some of these diagrams, some of them represent multiple wires. Often one wire represents one signal, but sometimes, for instance, for data or address, there's a lot of wires, maybe 32 or 64. So instead of representing 64 different lines in a diagram, we'll just show a box, and the box will be clear if there's valid data, and it'll be gray if, well, we don't know what it is, or it doesn't matter what the value is at that time. So here shows a picture of how the system might be able to read information. It starts at time 1, where the system decides it's going to want to read something. So during the first time period, it puts the address on the bus and tells the system that it wants to read from memory. And then it waits for a while. Eventually the data is available, and at that point the system will signal that the data is available, and the memory will put the data on the bus so that it can be viewed by the CPU and copied into the CPU. You note that there's a time in between where nothing seems to be happening. That's a wait state in there. A block transfer might request the memory at one time period and then have a wait state where nothing's really happening, maybe multiple wait states. And then at some other point, it'll finally start to transfer the data to the CPU in multiple transfers. In other words, there's the first data block, the second data block, the third, the fourth data block shown here. Oh, that's the end for now, but watch out. There's another lecture on bus. View the next lecture to learn how we calculate bus timings.